Welcome to This Explainer. Today, we're diving straight into a heavy machinery murder mystery to learn exactly how to move from a catastrophic breakdown to a permanent systemic fix. If you've ever dealt with equipment failure, you absolutely know the frustration of fixing a symptom only to have that exact same machine break down again next week. Well, today, we're going to learn how to stop that vicious cycle completely. Okay, picture this crime scene. A massive Komatsu HD-785-7 haul truck, an absolutely critical piece of heavy machinery, just suffered a sudden, incredibly expensive engine failure right in the middle of a shift. Operations literally grind to a halt. Now, the immediate instinct is usually just to swap out the engine and get that truck back to work, right? But how do we guarantee this exact failure never happens again across the entire fleet? To do that, we have to treat this like a real crime scene and bring in the proper investigative tools.
Chapter 1. Mapping the usual suspects.
So we can't actually fix the engine until we map out every single thing that could have gone wrong. To organize our suspect pool, we look to the past, specifically to a brilliant Japanese chemical engineer and statistician named Kaoru Ishikawa. Back in the 1960s, while working at the Kawasaki shipyards, he developed a visual tool that became foundational to modern quality control. He realized early on that to truly solve a defect, you have to visualize how every single system, process, and person interacts. It's just not enough to look at the broken part. You have to look at the entire environment that actually allowed it to break in the first place.
Let's break down the actual anatomy of this diagram, which is commonly called a fishbone diagram. You start with the head on the far right, which is the specific failure of our Komatsu engine. From there, you draw the spine, extending horizontally to the left. Branching off that spine are the bones, representing the major categories of potential causes. And finally, you add the ribs. These are the smaller horizontal lines branching off the bones to list specific granular issues. It is a brilliant way to visually break down a complex engineering problem so that everyone, from your frontline workers all the way up to management, can easily understand it.
Now, you might be wondering what exactly goes on those bones. That's where the 6M's framework comes in, and it guarantees no stone is left unturned. Consider the machine itself. Was it a cracked oil pump? What about the method? Were maintenance intervals stretched a little too far? Was it the material, like using the wrong viscosity of oil? Could it be manpower, where maybe a technician just rushed the assembly? What about measurement? Did a faulty gauge give a false normal reading? Or even Mother Nature? Did extreme ambient heat play a role? By forcing your team to brainstorm across all 6 of these M's, you map out every potential cause before anyone even picks up a wrench.
Chapter 2. The interrogation.
With our broad list of suspects mapped out, it's time to systematically hunt down the actual killer. We have to move from brainstorming to hard investigation, gathering physical evidence before we really begin our interrogation. First, we prioritize the top 2 or 3 most likely causes based on the unit's recent history. Second, we verify with data. We move from theory to fact by getting out into the field, pulling backlog history, or checking those condition monitoring reports. Third, once the data confirms a specific parameter, we apply the 5 whys methodology to drill down to the absolute root cause. And fourth, we develop a corrective action plan to implement a real solution. Let's zoom in on step 3 for a second, the 5 whys. We start our rapid-fire 5 whys interrogation by asking the most obvious question about the engine's death. Why did the engine fail? Well, our field data gives us the answer, because it overheated significantly while pulling a heavy load up the ramp. That is our first physical symptom, but we definitely can't stop there. We push past those first physical symptoms, tracking the cascading mechanical domino effect. Why did it overheat? Because the coolant dropped to a critical level, causing a total loss of cooling capacity. Okay, right, but why was the coolant level low? Because the lower radiator hose ruptured, dumping all the coolant. Now, if we stopped right here, we just replace the hose and send the truck back out. But we have to know the why behind the rupture. And here is the dramatic reveal. Why did the hose rupture? Because it had been rubbing against a loose frame bracket, which slowly chafed right through the rubber. So the ultimate question, why was the frame bracket loose? Because the retaining bolts were not torqued to the OEM specification during the last 1,000-hour preventative maintenance. The mechanic relied on feel rather than using a torque wrench, and standard operational vibration just backed the bolts right out. The absolute root cause here isn't a broken hose. Actually, it's a procedural gap.
Chapter 3. Enforcing the permanent fix.
Finding that root cause is really only half the battle. Now we have to lock that killer away forever using what's called a PICA table, which stands for Problem Identification Corrective Action. Notice how the actions are split up.
We don't just list the problem and the root cause we just discovered. We clearly define exactly what needs to be done, assign a person in charge, the pick, and set a hard due date. A maintenance planner uses this tool to force the team to move beyond just talking about a fix, turning it into an undeniable, scheduled mandate.
Listen, if you take away absolutely anything from this explainer today, let it be this. Fixing the symptom gets the truck running, but fixing the system saves the entire fleet. The corrective action is your immediate fix, replacing the hose in the blown engine. But the true value lies in the preventive action. By updating the PM checklist to mandate torque wrench use and adding a QA/QC sign-off by a lead mechanic for critical fasteners, we ensure that the other trucks in our fleet don't suffer the exact same fate next week. We are upgrading the entire system.
Chapter 4, Measuring Real-World Success. All right, once those new procedures are in place, the job shifts from investigation to monitoring. We have to track proactive leading indicators to ensure the new rules are actually being followed, and lagging indicators to confirm the equipment is genuinely running better. Let's break this down real quick. Leading indicators tell us if the process is working before a failure even occurs. Are the newly updated PM checklists being completed on time? That is your PM compliance. If that drops, your preventive actions aren't happening. Lagging indicators, on the other hand, are the classic reliability metrics. Mean time between failures, or MTBF, is the ultimate metric here. If our preventive action on the Komatsu truck actually worked, the MTBF for the cooling system across the entire fleet should steadily increase and our unscheduled downtime should drop.
By running a quarterly 80-20 Pareto chart straight from your maintenance software, you can actually visually track your targeted cooling failures shrinking. Over time, that huge slice representing cooling system failures should fall off the chart entirely, replaced by new, hopefully less critical issues. But remember, patience is absolutely key here. The lag time between implementing a PICA and actually seeing the MTBF improve can be anywhere from 3 to 6 months. Do not abandon a brilliant new preventative strategy after just 4 weeks, just because the overall breakdown rate hasn't massively shifted yet. As we wrap up this explainer, I want to leave you with a question to challenge your own operational processes and really encourage you to investigate deeper. If your top piece of equipment failed tomorrow, would your team just replace the broken part, or would you interrogate the system that allowed it to break in the first place? By using the Ishikawa diagram, the 5 whys, and a strict PICA table, you transform from a reactive mechanic into a proactive investigator. You don't just fix machines, you fix operations. Thanks so much for joining me on this explainer. Keep asking why.